Hello everyone, it's your AP tutor here, and today we're going to be looking at implicit differentiation in Calculus AB. Now, what's the whole point of implicit differentiation? Well, time and time again in calculus, we're asked to find dy dx, right? We're asked to find the slope. For example, a lot of the times we're given something like this, right? And then they want us to find the slope of this function when x is equal to 1. And we did that by taking the derivative of both sides, and that gives us dy dx equals 4x, and we plug in x equals 1, and then we find out that the derivative, or the slope, at x equals 1 for this original function is 4. Nice and simple. But what happens when y isn't isolated nice and pretty on the left side of our equation like this? What if y is stuck inside? For example, what if our function looks like this? Well, we can try the same approach, right? We can isolate by solving for y first, and I can do that by moving x squared to the right side and then taking the square root of everything, and that gives us all of this. And then I can take the derivative of this function and then plug in and whatnot. But as you can see, it's already a total mess. But this is why we want to use implicit differentiation, because it allows us to solve for dy dx without solving for y first. That makes things a lot easier. So let's move this up here. We begin by taking the derivative of everything. And this is what the notation looks like. Some teachers can be pretty particular, so if you want to get all that partial credit, I would just make sure to be doing this on everything, okay? And this just means we're taking the derivative of everything with respect to x. Well, what does the first step look like? Well, you've done this a couple hundred times. It's going to be 2x. What is the derivative of y squared? Well, that's 2y. But the trick with implicit differentiation is when you take the derivative of y, you need to make sure you leave behind a dy dx. The reason why this exists is because of chain rule. All right, and then the derivative of 50, well, 50 is a constant, and so that's going to give us 0. All right, so now what we need to do is solve for dy dx. Okay, and I'm just going to do that by moving 2x to this side, right? And this is 2y times dy dx, so I can just divide both sides by 2y. And that gives us 2x over 2y with a negative. Nice and simple, right? Okay, let's take a look at some more examples. All right. Let's do the square root of y minus sine x is equal to 2. And let's begin by using implicit differentiation, right? And so I write it like so. The derivative of the square root of y with respect to x subtracted by the derivative of sine x with respect to x is equal to the derivative of 2 with respect to x. All right, what's another way to write square root of y that makes it easier for us to look at? Yep. Well, the square root of y is y to the power of half, 1 over 2. And so that makes the derivative just a little bit easier to do, at least for me. So you bring the top down, subtract it by 1, and that gives us this. And remember, we're doing the derivative of y, so we need to leave behind a dy dx. All right, what's going on next? Well, it's the derivative of sine of x, and that's cosine x, is equal to 2. Oh, sorry, is equal to 0 because 2 is a constant. All right, and then we solve for dy dx. is equal to cosine of x. We're moving the cosine to the other side, and then we are dividing both sides by 1/2 of y negative 1 over 2. And let's just do some rewriting to make it nice and pretty, and that gives us 2 square root of y cosine of x. All right, very nice. So that's the answer that we got this way. Let's take another look at implicit differentiation through this other example, and specifically why we were seeing that dy dx earlier, right? So this is the problem that we'll solve. X times y squared plus y cubed is equal to 5. Now, as you see, y is totally stuck inside of our equation, and it's going to be hard to isolate, right? So that's why we're going to be using implicit differentiation. And every time we write y is just another way to write f of x, right? F of x meaning a function of x, right? Y is a function of x. Okay, so let's substitute y for f of x. All right, x times f of x squared plus f of x cubed is equal to 5. All right, now let's do the derivative of this. Well, the first thing that we're going to do is product rule, right? And that gives us this, x times the derivative of that, so we're going to be doing chain rule here, right? Derivative of the outside function times the derivative of the inside function. That's f prime of x, right? Now the second half of product rule gives us this. All right, and then the derivative of f of x cubed, again, we're doing the derivative of the outside function first, times the derivative of the inside function, which would be f prime of x. All right, and as we agreed earlier, y is equal to f of x. So dy dx, the derivative of y, is equal to the derivative of f of x, right? And so now let's substitute back all of our f of x's and f prime of x's for y's and dy dx's, right? So that's x times 2y, this is times dy dx plus what we have in here, right? That's y squared plus 3 times y squared times dy dx is equal to 0. Now we have the dy dx's inside the equation, and hopefully that helps you understand why we put those down in the first place, because of chain rule. All right, and now let's continue to solve, right? And we want to isolate dy dx, so let me just make this a little bit prettier first. Little bit prettier first. Okay, so I'm gonna keep my dy dx's on one side, and then running out of space, but you factor out your dy dx, 2xy plus 3y squared is equal to negative y squared, and then you can divide both sides by this to finally give us our isolated dy dx. There we go. And congratulations, you now know how to do implicit differentiation. And implicit differentiation works whether our variables are x and y, or let's say a and t, right? Sometimes your teachers might throw a curveball at you. They might give you a to the power of 4 minus t to the power of 4 is equal to 6a squared t, right? But they will always tell you how they want you to take the derivative, right? They might ask you, solve for dA dt, right? Think back to what we did before, right? We were solving for dy dx. All right. So in this case, a is the equivalent of y, and t is the equivalent of x. And let's just sort of keep that in mind, right? Okay, but let's go ahead and get started. They want us to differentiate everything with respect to t. So let's just write that out really quickly, right? d dt times a to the power of 4 subtracted by d dt, d to the power of 4 is equal to d dt times 6a squared times t. All right, and now let's do our derivatives. 4a to the power of 3, and we need to add on that dA dt, because remember, a was our equivalent to y, right? And you would always add on that dy dx, okay? We're deriving with respect to t here for this next one, so we don't need to stick on that dt over dt, right? And then at the end, we're going to be doing some product rule. Very fun. Okay, 6 times 2, 2a dA dt times t plus 6 times a squared. All right. And now let's just simplify this all a little bit more. dt minus 4t cubed times 12a t dA dt plus 6a squared. All right, and now what do we do, right? Same thing as before. We want to isolate our dA dt. And so I do that by bringing it all to the same side. 4a cubed dA dt minus 12at dA dt is equal to 6a squared plus 4t cubed. All right, and again, we just factor out our dA dt. It's 12at is equal to 6a squared plus 4t cubed. And we divide both sides by that. Our final answer is dA dt is equal to 6a squared plus 4t cubed divided by 4a cubed minus 12at. And remember, in AP Calculus, you don't actually need to simplify to the absolute maximum in all of your answers. And that saves you a lot of time on the AP test. And that also saves you the potential to make some pretty critical mistakes when you otherwise solved everything right. But hopefully all of this clears up implicit differentiation, and good luck with your exams.